So last time we started to talk about how to design FIR filters, okay, finite impulse response filters. And last time we were mostly talking about FIR filter design via what I would call different kinds of least squares, or possibly interpolation techniques, right? That meant that what I said was I specify a set of points in the frequency domain, and if I have the same number of points as I have filter coefficients, then I can force my frequency response to go right through those points. And if I have more points than I have taps, then what I'm saying is I want you to do as well as possible on these, greater than number of taps points, right? Get me as close as possible to what I specify at those points. The problem is that we can't really control what happens between the points that we specify, right? So, for example, when I have kind of an interpolating filter, right? So, for example, we kind of looked at pictures like this. If the filter exactly interpolates these values, then I can't really do anything about what happens between here and here, right? I mean, yes, I can force the filter to go exactly through these points, but the ripple, that is very nice, the deviation from the ideal response is something that I can't really control, okay? And I can try to solve that problem a little bit by specifying more points, saying, hey, you got to do well all the way through these points here. But in that case, again, I may do something better, but I still have really no control over the actual response, right? In this case, I'm not even interpolating the points I ask for. I'm just getting an approximation of those points. So the topic of today's lecture is forcing the filter to not deviate more than a certain amount that we ask for in the pass band and the stop band, right? And so, so the upshot of this is we can't control what happens between the points. And so remember, what I talked about last time was when I'm designing a filter, there are a bunch of kind of just general steps, right? One is I decide what is the type of filter I'm willing to tolerate, like a length 23 FIR filter. And then one of the next things is, how do I measure how good that filter is? How do I measure the error of that filter compared to the ideal frequency response, right? And in that case, what we're going to do here is we're going to change that error measure. So instead of looking at a least squares kind of error measure, where I'm looking at the sum of a bunch of square differences, instead, the error function I'm going to consider is I want to minimize this error, which is defined as the maximum difference between the amplitude that I got and the amplitude that I want. Right? That's like saying I want to force that deviation to be as small as possible, right? And that does, I mean, in this sense, there are no samples anymore, right? All I'm saying is you've got to be as close as possible to this amplitude response. And it turns out that filters that are optimal with respect to this criteria are called Equiripple. And this criteria here is called the Chebyshev error criterion, or this is called Chebyshev approximation. And so an Equiripple filter looks basically like this. So if this is my ideal amplitude response, then what I have is some band, and the filter nicely oscillates inside this band. And it's called Equiripple because the maximum deviation in both the pass band and the stop band never goes outside these dotted lines, and the maxima and the minima exactly hit the dotted lines, right? So unlike some of the filters that we designed last time, there is no kind of like extreme difference between where the filter might go in the pass band. I have this kind of nice, steady, equally sized ripple. And as you can imagine, that kind of thing could be good. If I want to ensure that nothing too weird can happen in the pass band or the stop band, I can kind of, as we'll see, specify, okay, I can tell you what I will tolerate here and what I will tolerate here. And then as long as my filter size is compatible with those specifications, I can drive the filter response down to be exactly what I want. Okay, and so the way that we're going to set up this problem is as follows, right? So I'm going to say, an acceptable frequency response has the following characteristics. I have to have, basically, we're going to look for linear phase FIR filters. Okay, so we learned about those last time. Again, we like linear phase filters because the effect is simply to delay the output of the signal, right? And a linear phase FIR filter turns out to have this very nice filter structure, which means that the filter is real and it has symmetry around its middle value. Either it has actual symmetry, meaning like it's kind of even around the middle, or it has this odd symmetry, which we didn't really talk about too much last time, but we learned there are these type 1, type 2, type 3, type 4 filters that all are linear phase, right? And some of them would be good for low-pass filters, and some of them would be good for high-pass filters. And since I'm mostly motivating all this with low-pass filters, I'm kind of sticking with type 1 filters for most of these lectures. Okay, so linear phase, we can specify the width, let me call that delta F, of the transition band. Right, so let me just go back to this picture for a second. So the transition band, right, here, again, just like for the other case, what I'm going to do is I'm going to say, okay, this here is the pass band, this here is the stop band, and then I may define a transition band where I let the filter gracefully go from the pass band to the stop band. And so this width here I'm going to call delta F, okay? And of course, the smaller delta F is, the more stringent the specifications are on the filter, right? That's like saying you got to really book it from the pass band down to the stop band. And probably to do that, I'm going to need a lot of filter taps. Okay. So I specify the width, and then I specify the deviation from 1 in the pass band of plus or minus some number, delta 1. And then I can also separately specify the deviation from 0 in the stop band of plus or minus delta 2. Okay? And so where I'm going to end this whole lecture is basically a recipe that says, okay, if I give you these three numbers, how would I determine what the necessary length of the filter is, for example? That would let me be minimally satisfactory. Okay. And so one thing that we kind of proved, or I don't know if we proved it, we certainly talked about it last time, was the amplitude response of a, let me say a type 1 linear phase filter can be written as this. A of omega is equal to the sum of a bunch of cosines, each of which has a certain weight. And again, this R I'm going to define as n plus 1 over 2. Right, so here what I'm saying is I can write, the amplitude response as these nice cosines, and that's why when you look at an amplitude response for a filter, it looks basically like, wiggliness, right? I mean, the sum of the cosines definitely doesn't make it something that has like a kind of a obvious constant frequency, but this kind of oscillatory behavior comes from the cosines, okay? And we showed why this was, or how this was true last time. In fact, we gave an explicit formula that said, how are these coefficients on the cosines related to the filter taps, right? So here I'm being a little bit more general and just saying that the amplitude is some sort of sum of cosines, okay? And so now what I need to do is solve an approximation problem where I've got some desired frequency response and I want to minimize this deviation where this amplitude response has that form of a sum of cosines, okay? So I'm going to call that the approximation problem. So what I'm going to assume is, and this is actually a more general theorem than even what I need to design here. So given a set of frequency bands in this 0 pi range. So for example, in our case, I'm kind of saying, okay, here's the pass band, here's the stop band. But in general, I could actually specify more bands. I could make the filter make a bunch of other things in there if I wanted to. And then I give you a desired real valued A desired at omega in these bands. And then I give you a positive weight function, right? This is basically telling me how seriously do I care about approximating the desired amplitude response in each band, right? So I could say, dude, I really care about the pass band, I don't care so much about the stop band, or vice versa. This weighting function allows me to do that. And then I have the form of A omega, which we just showed on the previous slide was going to be the sum of cosines. So the goal is find these multipliers, right? So that's what we're going to do. Again, this is one of these things where I'm basically going to expose the theory of this thing throughout this lecture, but then there's like a one-line Matlab command that does this for you, right? So it's like I have to do this manually every time you want to design a filter. This is just like what goes on under the hood, okay? And so the theorem that lets us know how we can solve this problem is kind of interesting. It's called the alternation theorem. So we solve using the alternation theorem. Which I'm not going to prove or anything like that. But basically it says that if my amplitude response is a sum of R cosines, then a necessary and sufficient condition for A of omega to be the unique best weighted Chebyshev, which means Equiripple, approximation to my desired frequency response or impulse response on the given bands, is that this error, which I'm going to define as this weight function, and this is basically the absolute difference between what I want and what I get. This error has to exhibit at least R plus 1, what are called extremal frequencies in the given bands. And so what is an extremal frequency, right? An extremal frequency is basically saying that I have achieved the maximum error, okay? So somewhere along this line, if you look back at my kind of picture, here's my picture that says my amplitude response is kind of bouncing back and forth between the dotted lines, right? And what this is telling me is that if I count the number of places where I hit the dotted lines, that I have to have at least r plus one of those, where r is the number of cosines I'm adding together, okay? And that's kind of a neat theorem, because it tells me that if I can find a function that indeed bounces back and forth along the dotted lines the right number of times, then I'm done, right? It turns out that is necessary and sufficient to be the best possible function. And it turns out that function is unique, okay? So the proof of why this is true is a little bit complicated. Let me just draw what I just kind of verbally said in a different way. So extremal frequencies are a set of places such that the error at each of these places is equal to the maximum error, okay? And it also says that the error has to kind of bounce back and forth between positive and negative. Right, so let me draw this again. So let's suppose, for example, that I have a n equals 13 length FIR filter, okay? So my R is going to be 7, right? I'm going to have 7 cosines. And what this is telling me is that if my desired amplitude response looks like this, so kind of here's my transition band. So what this is saying is that if I draw in my maximum dotted lines, that I have to get something that looks like this. Looks kind of crappy the way I drew it, but So let's count why this would work, right? This is like saying, how many extremal frequencies do I have? Well, I have 1, 2, 3, 4, 5, 6, 7, 8, right? Because here I have r plus 1, number of cosines plus 1, places where I'm exactly hitting the dotted lines, okay? And one thing to remember is that, most of these places are actually kind of maxima or minima, local maxima or minima of the curve, but there are a couple places here, like when I'm going from the pass band to the stop band, again, my error here is exactly on the dotted lines, but then I kind of keep on going, and here again, the error is between here and here. But the thing to remember is that I'm only looking at the maximum error in the bands that I specify, right? So here I basically get the biggest errors at the end of this band, and then again at the beginning of that band. Okay, so that means I need to have 8 extremal frequencies. And if I recognize that kind of function, then I can stop and say, well, whatever this is has to be optimal. Okay, so let me stop and ask if there are any questions about the big picture. Okay, so now the name of the game is, how do I find these r plus 1 extremal frequencies that I know I need, right? And the answer to that is an algorithm called the Remez exchange algorithm. Okay. So we're going to do this in a kind of an iterative way, right? So this is basically like an iterative algorithm where we guess what those extremal frequencies might be, and we keep on trying to refine them until we end up with something that satisfies our constraints. Okay. So here is kind of a lemma, right? Kind of a baby theorem. So if I look at my error, right, my error is defined as the difference between the desired frequency response and the sum of these R cosines. So this thing can be made to take on the values plus or minus delta for any given set omega 1 through omega r plus 1. That is, I can say that my desired amplitude at these frequencies is equal to the actual thing that I got, which is my sum of cosines, plus, this error, which is bouncing back and forth between positive delta and minus delta. And I guess I should say this is I. And this I can go from 1 to r plus 1. And so the idea is that this has a unique solution for, ck, k equals 0 to r minus 1, and delta, right? So what is the interpretation of this lemma? What this is saying is, if I tell you, well, actually, the way to think about this is, if I say, okay, I tell you the error that I want and the CKs, actually, maybe it's better to say it the other way. So if I tell you the omega r's, right, then there is some set of cosine coefficients and a delta such that the error bounces around nicely between these values, right? And the way I think about this is that these are like the r plus 1 givens, and these are like the r plus 1 unknowns. So it's kind of like, stands to reason if I have r plus 1 equations and r plus 1 unknowns, that I can solve that system uniquely and find out the CKs and the delta that make this work, right? So it's kind of like saying, okay, between 0 and pi, I can hypothesize that these r plus 1 frequencies are going to be the extremal ones. Then I solve this, for the CK, for the delta, and I look and say, okay, so did that work? If it did work, I'm done. If it didn't work, then I guess some more frequencies, right? That's kind of the mechanism that we're going to take. Okay, so I'm not going to prove this other than to say that it kind of stands to reason that if I have r plus 1 givens and r plus 1 unknowns, that I can make this work. Okay, and so here's how the Remez exchange algorithm works. So I'm going to give this little guy an asterisk to remind myself this is a thing I can solve. So here's the way it works. First, I, am given a set of initial guesses. So this is like my initial guesses for the extremal frequencies. Right? Sorry. And, I could just initially guess them to be evenly spaced across the 0 to pi band if I wanted to. Or if I, don't have a transition, if I have a transition band, then I would say I space half of them in the pass band, half of them in the stop band. Let's see what happens, right? So then I basically solve the linear equations in that system I gave you before, and that means that the solution has an error that oscillates between, oscillates with amplitude delta, and I'm going to kind of say this is going to be like a iterative thing. So I'm going to say that I have an error at a given point delta, and I have a set of points tk. So that I can do for sure. So I find out, okay, So what was my extremal error? And now I can say I'm going to interpolate that frequency response to find what happened at all the rest of the frequencies. And then I'm going to see, am I done? Right? So I'm going to search 0 pi to see if and where the magnitude of the error is greater than what I landed with here. And then if the maximum error is equal to what I got, then I'm done. Otherwise, I take the places where I have the most error, the r+1 maximal error points as tk plus 1, and then I iterate. So all I'm doing is I'm basically choosing some points, making the frequency response do what I want exactly at those points, seeing if those are really actually the places where the error is the greatest. If they're not, I just find out what the greatest error points are in my current set, and I keep on iterating, right? And the exciting thing is, we'll talk about how and when this converges in just a second, but this is the basic idea. And this is actually something that you could do painfully by hand, right? So I'm going to do one example of this by hand on a very simple case, just so you can kind of see what's going on under the hood, okay? So let me stop and ask if the basic idea kind of makes sense. And this is actually not a very unusual way of posing a signal processing or a computer vision kind of problem where you say, okay, I have an initial guess, I have a cost function, I see how good I do, and if I don't like my, I keep on refining my initial guess until I get to the minimum, right? That's how a lot of numerical minimization algorithms work. Okay, so here's an example. And the example with the cosines is a little bit tedious to do by hand because there's lots of trig involved, and I don't want to really get into cosines of weird numbers, right? But there's actually, as a side note, a cute little theorem that says that cosines and polynomials are equivalent. So I'm going to say, side note, the sum of cosines is basically equivalent to a sum of polynomials, which are a lot easier to work with using a change of variables. And so for those of you that are mathematically inclined, what I'm going to do is I'm going to say I am going to define a new function of x where it's the amplitude of the inverse cosine of this angle, right? So what that means is that I'm taking my sum of cosines like this, the kind of cool thing is that this thing here, if k is an integer, turns out to be a polynomial in x, which you wouldn't expect. So this actually turns out to be a polynomial in x. These are called the Chebyshev polynomials. So you can see why it's true for, for k equals 0, it's true because its cosine of 0 is 1. For k equals 1, it's true because cosine of cosine inverse of x is x. And then you can prove that there's a recursive formula that tells me what the next polynomial is given the first two. So you kind of find out why this is true via inductive proof. We're going to just kind of take that for granted, which means that this is a polynomial, which means that this whole thing turns out to be writable like a polynomial with different coefficients on the x. So this is going to make it easier for me to actually solve a problem for you in class, because then I don't have to actually evaluate the cosines of some weird angles. I just have to evaluate the polynomial in a certain place. Okay, so here's the example. So let's try to approximate the function x squared. So this is going to kind of play the role of my desired function of omega by a polynomial with two coefficients. And my frequency range is going to be from 0 to 1 instead of 0 to pi. And I'm going to use my Chebyshev error. Right? So this here is playing the role of my a of omega, and this here is playing the role of my a desired omega. So it's kind of like saying I've got a class of functions given by this, and I'm trying to do as well as possible to approximate some new given function. So really what I'm trying to do is I'm trying to minimize over the two numbers I get to change around the maximum error on this interval of the difference between what I want and what I have. Okay? And since I have two functions, that means I have to find three extremal points. Right? If I find a place where the error hits these extremes at these 3 points, then I'm done. And so here's how I'm going to just iteratively kind of grind through the Remez exchange algorithm to find out how that works. Okay? So I'm going to guess, because I don't know any better, maybe the right places are going to be at a quarter, a half, and 1. Okay? So I'm going to hypothesize that's where I think my error is going to be. Right? And so what does that linear system tell me? That's like saying that I'm going to try and make the error oscillate on these 3 points. So I'm going to try and make the error oscillate. So that's like saying that at these 3 points, I have what I've got and the error and this delta. I don't know this, I don't know this, I don't know this, but I do know the xi's. And so that turns into a linear system that says, you know, here's what I don't know. And on the right-hand side of this equation, I have xi squared. So remember that my hypothesis was a quarter, a half, and 1, right? So that means that on the right-hand side, my actual values of that function are a 16th, a quarter, and 1. And then I plug in, you know, what's multiplying d0, 1. What's multiplying d1? Well, it's the value of xi, which is a quarter. And then what's multiplying delta? So I'm going to assume that my delta at the first place is going to be 1, right? And then I have the other points. This is saying I now oscillate to -1. And then I say now I'm oscillating to 1, right? So this kind of here, this column is the oscillation. This is the constant term, and this is the x term. And so now I've got a linear system with 3 equations and 3 unknowns. I can solve for that and find out that I get d0 equals, as it turns out, -5/16. d1 is equal to 5/4, and the delta is equal to 1/16. And so what does that mean? That means that now I can plot the corresponding function and compare it to my desired function. So what do I do if I get that? Okay, so now I've got my graph that says, okay, over 0 to 1, here were my places where I guessed. And what I found out was that I could make the error differ from x squared by 1/16 at these points, right? So what does x squared look like? Actually, let me just plot the error, actually. So that's like saying the error at step 0 is x squared minus whatever I got. And I made it so that here are my points. I said, okay, you got to be here, yeah, got to be here, and you got to be here. And if I draw the rest of the function turns out to look like this, right? So if I kind of figure out what I actually got, it turns out that this is my actual shape. right? So yes, I was able to make the error equal to those constant values at these 3 points, but if I look at my actual result, I can see that it doesn't actually take the maximum error at those 3 points. There's a lot more error somewhere else, right? So the error is really big over here, and the error is more than a 16th over here, and the error turns out to be biggest in this direction at 5/8, right? So now I say, okay, well, I guessed wrong, right? Those 3 points originally were bad, but now I find the 3 places where I've got the biggest error now, and I would make my new guess would be, okay, I'm going to make the error take the biggest values at these places, right? That's my new hypothesis. And so the error here, the maximum of this error, is equal to 5/16. That's what happens over here. So this is not equal to my delta. That tells me I have more work to do, right? I didn't hit the maximum error at those places. So here's my new hypothesis, and now I'm going to do it again, right? So I'm going to set up the same set of equations. Now I'm going to solve this guy. So again, I have to figure out what are these new values here. The x squared values are going to be 0, 25 over 64, 1. And on this side, I'd have, again, the constant term, the x term, and the ripple term. I solve this again, and it turns out I get a different set of values. Okay. So, in some sense, this is actually, okay, so this is a different function, right? So now if I'm going to draw my function, I have to figure out, okay, what does this new linear function look like compared to the quadratic? So my error function, again, is going to be the difference between x squared and this new linear function. If I plot that over 0, 1, again, my hypotheses were this was the error, this was the place, and this was the place where the error took the most value. And I found out that now the value of that error is 15 over 128. So I was able to get this value here, and this value here, okay? And now if I connect the dots again, if I figure out what is the actual response, it turns out that it looks like this. So I'm getting a little bit closer, but the error at 1/2 is lower than the error at 5/8. Okay? So like this error is still bigger. And so this turned out to be minus 17 over 128. So the maximum error is equal to 17 over 128, which is still bigger than my delta. Okay? So now, again, I look and see, well, where are my biggest errors? Here, here, and here at 1/2. So now my next set is going to be 0, 1/2, 1. Okay? So now this is the final iteration. I'm going to do it one more time. I set up my equations. My hypothesis is again going to be 0, 1/2, 1, where the error bounces back and forth like this. Then I have x squared is 0, 1/4, 1. I solve these equations, and I get d0 equals minus 1/8, d1 equals 1, delta equals 1/8. So now, last thing I'm going to do is I'm going to plot my error function. It's going to be x squared minus 1/8 plus x. If I plot that function over 0, 1, here are my points, and I found out that I can make these points oscillate between plus 1/8 and minus 1/8. So I know that my function has to pass through here, here, and here. And when I compute the actual function, it turns out that what I get is this. And now I stop and I say, we're done, right? Because the function doesn't get any worse than 1/8 at any other point between 0 and 1, right? And I found the 3 points where it bounces back and forth. So since my maximum of the error is equal to my delta, I'm done. Okay, so the best approximation is this function x minus 1/8. Right? So that is the that is the essence of the Remez exchange algorithm, where I'm basically guessing some values, cranking through to see am I actually extremal on those values or not. If I'm not, I find the maximum values, I try those instead, and I keep on doing it. And you could argue that if I was smarter and if I had chosen 0, 1/2, and 1 at the very beginning, then I would have been done on the first step, right? I would have guessed correctly and life would have been good, right? So you could get lucky. Life is like that. Okay, so before I show you some Matlab examples to show you how this works, let me just stop and ask, so does this iterative process always work? And the answer is kind of yes and no. Yes, in the sense that you can always get the Equiripple filter to converge on a set of extremal frequencies. So you can always obtain some Equiripple filter. But the thing I haven't talked about is how do you force that Equiripple filter to satisfy the constraints in the passband and the stopband that you gave in the very beginning, right? The problem is that it may not be possible to satisfy those constraints given the number of filter taps that you asked for, right? So does Remez always work? So it does work in the sense that, yes, it always converges to an Equiripple approximation. But it may not have the passband, stopband characteristics you want for a given n. Right? There are just some inherently, there are just some issues that you can't skate around, right? So I mean, I can't make this ripple arbitrarily small if I only give you 3 filter taps, right? I mean, I can only do so well with fixed amount of information. And so one nice thing is that there is a kind of there are a whole bunch of heuristics for if I give you 3 of these specifications, how do you find the 4th, right? So here's one kind of simple heuristic. And this is not the only heuristic, but this is the one that I have written down. So if I'm given n, which is the filter length, and I'm given the passband and the stopband edges, and I'm given the deviation in the passband, from the ideal value of 1, and I'm given the deviation in the stopband from 0, then these numbers are all related in the following way. So there's some crazy formula. Not that you have to write this down or remember it. It just looks like some random formula. +1. Okay. So let's just think about what this means, though, right? So what this means is, for example, as I bring the passband and the stopband closer together, that means that this number is getting smaller. That means the n that I need gets bigger, right? So that's like saying that if I want the transition between the passband and the stopband to be really steep, I need a larger n. And in the same way, if I want the deviation to be really small, right, that means that this is going to be some, small number. It's going to be less than 1, right? So log 10 of that is going to be some negative number, and negative 20 times that is going to be some big number, right? So the smaller I want this, the bigger the numerator is going to be, right? And so this kind of gives you a rule of thumb where if I know these specifications, I can solve for n, and then I find the best n that works for me, right? And then kind of there are kind of reverse things. If I say, okay, I can't change my n, and I can't change my, say, deviation from the stop band, what's the best passband ripple that I can expect to achieve, right? So those kinds of trade-offs are represented in other heuristic formulas, okay? And Matlab has a bunch of these things built into it, okay? And so the nice thing is that I can use a function in Matlab called firpm to design Equiripple filters. And of course, this is what you all came here to see, right? What is the magic Matlab formula that does all this stuff for you, right? This is also called the Parkes-McClellan algorithm. I'm not sure why Remez didn't get his name on the algorithm. Okay, so the PM stands for Parkes-McClellan. So let's see how this works, okay? So what I need to do for the Parkes-McClellan algorithm, so I need to define a set of passband and stopband regions, and then what I want the amplitude to be in those regions, okay? And so the way this works is that I specify some, how do I do this? I specify some edges like this, and then I specify some values like this. This is saying that between 0 and 0.3, I want to have a passband value of 1. Between 0.5 and 1, I want to have a passband value of 0. And here, these edges are really this times pi, right? So really what I'm saying is I want a passband edge of 0.3 pi and a stopband edge of 0.5 pi. Everything in the Matlab world is kind of normalized by pi, okay? And then my filter is designed by calling firpm. Of course, I'm probably going to screw this up. I think first I asked for, actually, it popped up the help for me, and I just ignored it. So I tell it what is the number of filter taps I want. So I'm going to suppose I want like 13 filter taps. And then I'm going to give it my edges and my values. And hopefully this will work. And so, again, if I were to look at the filter it gave me, this thing is producing for me a linear phase filter. Actually, I guess that what this does is it makes a length n plus 1 filter. So I guess if I wanted a length 13 filter, I should have put in 12 here. And then that will give me a type 1 filter, right?
Taps.
Hmm?
The taps are the line plus 1? Or,
yeah, so the number of taps I get is 12 plus 1. I'm not sure why they did it that way, but yeah. Because here, yeah, so when I asked for 12 here, I got a 13 tap filter. And I can see this is a linear phase filter because it's symmetric around the middle, okay? And then I can look at what is the, so I can compute the frequency response of this filter. And again, I need to define some places where I care about looking at this. So I'm going to say 500 points between 0 and pi. And then I'm going to look at my frequency response, b, comma 1, comma w. So what I'm doing here is when I do freq z, what that is doing is giving me the frequency response where I specify the numerator of the filter and the denominator of the filter and the frequencies where I care about it. Since this is an FIR filter, the denominator of the filter is 1, right? There is no denominator part, so that's why I have 1 in the second thing. And then I can look at the plot of my omega versus the absolute value of my frequency response. And you can see that this indeed gives me a Ripley filter. And I have a little function that I wrote that makes the visualization a little bit easier. So let me show this. So extremals is a function that I wrote. And here what I see is the, I guess I kind of screwed up extremals for some reason, because these are not, This guy here is not a extremal frequency. Bad Radke. Error, bad. Okay, so what was the thing I was doing yesterday? Oh, I think that what I was trying to do, let me try something else. So let me make different edges. I don't know why that wouldn't work, actually. Another one of these cases where it worked great at home. Maybe I was using a different frequency, filter length. Oh, I was using 14. Okay. So it worked for 14. It's still wrong. Why do I suck? So ignore this red dot here. Let me just go back to my extremals for a second here. What doesn't it like? Line 39. Comment out the offending thing. At least now it doesn't give me an error, but I think this thing is wrong because I, at 6:30 this morning, made an edit to this Matlab file that was wrong. I kind of hacked it together, if I'm being honest. Let's take this guy out. Better. Okay. So what I did here is I designed what did I ask for? I asked for a 14, so 14 plus 1 is 15 is the length of the filter, okay? And so now I have to figure out how many cosines does that mean. I think that means that I should have 9 extremal values. And so now let's count what I get. This one is extremal, and then I get this as 3 in the pass band, and I get 6 in the stop band. So here, and I think I outputted what that extremal value is, right? So I said here, m, the maximum deviation, is about 1/10. And so if I look at my response, I can see that, yes, this number here is right at 1/10 where I'm getting the error in the stop band. And then in the pass band, my errors are kind of, this is like 0.9, this is 1.1, this is 0.9, right? So I can kind of see that the error is bouncing around in the right way. And now, if I start to be a little more stringent, right? So here my edges were, I was saying the pass band was fairly narrow, right? And so if I said, okay, I don't like the fact that this, transition region is, I don't like the fact that the ripple is so large, right? So what can I do to reduce the ripple? Well, if I widen the transition region, I would give the filter more room to breathe, and the ripple should be smaller, right? Because then it can kind of suck up some of the approximation error in the transition band. And so I could say, okay, what if my edges were between 0.3 and 0.5, and then I redesign my filter with those values. So now I can see that, indeed, I get a much closer filter to the amplitude response in the pass band and stop band at the expense of having made this transition region wider, right? So my ripple is less, but my transition region is longer. And kind of conversely, if I tried to really drive it through and say, okay, I want you to go from the pass band to the stop band in this amount, 0.3 to 0.32. Oops, I forgot to actually design the filter. So now my error is going to be very large, right? And so again, I kind of screwed it up because there should be an extremal frequency over here. So now there's like a huge variation in the pass band and the stop band, and this would be an undesirable filter, right? So what I need to do instead would say, okay, well, if I'm going to put those kind of constraints on it, maybe I should crank this up to be a length 25 filter instead. And now let's see what I get there. So now I'm a little bit better, and if I were to crank it up even more, say length 54 or 55, right? So the more that I increase the length, the more I'm reducing the error. And so, again, if I wanted to now say, okay, well, clearly maybe now my filter is getting too long, so I have to compromise on, okay, maybe I don't need the transition band to be quite so sharp. Maybe I can afford it to be, you know, a little bit wider. Now I redesign it. Well, now I've got a great Ripley filter where, you know, the deviation in the passband and stop band is very small, right? So filter design is a lot like this, where you say, okay, what am I willing to tolerate in terms of filter length, ripple in the passband and stop band, and width of the transition region, right? You can't get everything all at once, but you can get kind of 3 out of the 4 is the idea. Okay, so questions or comments about this? So what I want you to do on the homework is one problem where you're actually doing exactly the same thing. Just design me a filter that has these specifications, and then plot for me either by hand or by Matlab where are the extremal frequencies, and count them up and verify that you get the right number of them. Okay. Okay. So questions or comments about this? I guess I already just said that. Let me say one more thing, which is that and this is kind of a minor note. I'm not sure why I didn't say this before. But another way to think about FIR filter design is by pushing around the 0 locations. I just wanted to make one note about where the 0 locations for linear phase FIR filters are. So the idea is that if Z is a 0, then Z conjugate is a 0, and so is 1 over Z, and 1 over Z conjugate. And so kind of what you get are zeros that occur in a cluster of 4, right? So for example, that's like saying that if this is my unit circle, if this is a 0 of my filter, then so is this. 1 over Z is like reflecting this point through the unit circle, and then you get something like so is this, and so is this, right? So the zeros kind of come in groups of 4. Unless you had something, for example, like, you know, if I had something that was on the real axis, that would be like saying if this was a 0, then so is this, and the conjugates, you know, already exist as zeros, right? Or I could have, you know, if I have a 0 at 1, then I don't have any reflection, and I just have this function here. So basically, you know, generally they look like this. If they're on the real axis, they look like that. If they're on 1 or minus 1, they look like this, right? And so, in some sense, you could take any linear phase FIR filter and decompose it as the product or the cascade of a bunch of these canonical filters that have kind of one group of zeros each, right? And this comes back to the question of what is the best way to realize a filter in a given scenario, right? So in addition to straight out end taps, polyphase, you could also think about a cascade of filters that correspond to groups of zeros, right? That's another way of thinking about it. And again, when we talked about the Z-transform, about the intuition behind how do the zeros of a transfer function affect the frequency response, right? So I would look at this, for example, and I would say, this is like a high-pass filter because the zeros are kind of nailing down that fabric close to low frequencies, and as I go around this way, there's nothing to constrain that fabric from billowing up at high frequencies, right? So again, you can use the fabric intuition by looking at the zeros in the Z-plane to decide what that FIR filter is going to be doing. And an FIR filter doesn't have any poles, so there's no poles to worry about in this kind of thing. And so let me wrap up as a conclusion for FIR filter design. So there are kind of advantages and disadvantages. So FIR advantages are, you know, I can achieve exactly linear phase, right? And we showed that linear phase filters have this nice symmetric impulse response, right? You can't do that with IIR filters because IIR filters are infinitely long, right? That means that there is no middle point for an IIR filter that you can get symmetry around. And that means that IIR filters necessarily have some sort of phase distortion that you may have to deal with. It's easy to implement these filters in terms of different filter structures. So it's really easy to implement an FIR filter. They're easily designed. Yeah. And the methods are generally linear, right? So both the method we talked today, the Remez exchange algorithm, is fundamentally solving a bunch of linear systems, and the least squares method from Monday is also solving different kinds of linear systems, right? So it's easy to design these kinds of filters, and it turns out these filters are always stable because there are no poles. Okay. On the downside, I may need to have a very long filter. I may need to have a very large n to achieve good approximations to some frequency responses. Right? So you kind of saw just now that if I was really trying to get that transition band to be very steep for that Equiripple filter, I kept on cranking up the number of taps, and I still wasn't very happy with the ripple that I saw inside the passband and the stopband. And so I may not want to have, and one way I think about the number of taps is it relates to the delay that I need to be able to produce the output if it's a causal filter, right? So I may have to, I may not want to be able to wait for a 1,000 tap filter to finish doing its job before I get my first output. Especially if I'm doing something like real-time audio processing, right? I may not want to do that. So I may need to have very long filters. I may need many operations per output, and I may need to store many coefficients. Right? So the longer the filter I have, the more stuff I have to keep in memory, right? And these days, you guys have it easy. There's really not the same kinds of constraints that you had on embedded systems that they used to have in the 60s and 70s and 80s. But you still may want to be efficient about the way that you design a filter, and the delay may be large, which is what I was saying before, right? And so what you're going to hear about next time is IIR filter design, infinite impulse response filter design, which can be achieved with a small polynomial in the numerator and a small polynomial in the denominator of the transfer function that require generally much, much fewer coefficients and memory to do, and it can actually achieve very nice frequency responses with very low filter orders, right? And so you're going to see some examples of that next time. Just kind of as a preview, Matlab has a bunch of built-in tools to help you design filters. And so, trying to remember what the best one is. I think there's one called Filter Designer. Maybe Filter Design? Well, when in doubt, look at the help. So you can see here there's a whole section on analog and digital filters, digital filter design. And so here, these functions are all kind of stuff we were talking about, like Chebyshev 1, Chebyshev 2. Here are some FIR filters. I guess what I was talking about in the past couple of days were FIR1 and FIRPM. But then there are these guys here. Okay, here it is. filterbuilder, FDA tool, FE tool. So let's try filterbuilder. So here it asks me what kind of filter I want to design. So let's say I want to design low-pass filter. And now it gives me a little menu of stuff that I immediately got rid of. And so I can say, okay, I want an FIR filter. I want to have it, order mode probably means, get me the lowest number of taps for the given specifications. And then I can say I want the passband to be between 0.45 pi and 0.55 pi. And I want the stopband ripple here to be 60. This is already being an Equiripple filter. I can specify more options if I wanted to. And then it tells me also, it even lets me design how I want to realize that filter. And so if I say OK, then I get a low-pass filter here, and I could just look at it, right? So if I plot my frequency response, I guess I don't know what this thing is. Okay, so this is this kind of filter structure thing, and this, to be honest, is something I don't really fully understand in Matlab. I think that if I were to just look at the numerator of this, I would get what I want. Again, this is me using MATLAB poorly because I'm sure that this filter structure is easy to use if I know the right function. So here is the filter that I designed, and again, it gives me something that satisfies my stop band requirements and gives me the right pass band and stop band location. And the one thing that I don't think I specified the pass band ripple. If I wanted to do more, so this filter, what was the other thing? FDA tool, yeah, that was the one. Right, so FDA tool is even a little bit nicer of a GUI, right? So here I'm saying, it kind of shows me schematically what these numbers mean, right? Pass band, stop band, and ripple. And then I have a whole bunch of choices here where I can say, do I want it to be Equiripple? Do I want it to be least squares? I can specify the order. I can specify the pass band and the stop band. And then once I'm done with that, I can design it. So I guess, why am I not able to design it right now? Okay, so let's design that filter. And then it shows me the magnitude response. There's also a similar tool called FV tool. I think that that's kind of like partially what you see here. I guess I have to call FV tool with a filter. But anyway, this is the kind of thing. I believe that there used to be, I actually worked at the MathWorks for 2 summers back in the day, and one of my jobs was to design the precursor to this function. And I thought that the one I designed, there was a way that you could actually drag the pass band and stop band ripple around and actually make it redesign on the fly. Maybe there's a graphical way of doing that here that I don't know how to do. But yeah. But this has like a whole ton of stuff built into it. So I mean, to be fair, when you're designing a filter in the real world, you don't need to do all of the manual setting up of the equations that I talked about in the last 2 lectures. This has got everything built into it. But I think it's important to understand what's under the hood so that you can kind of intelligently use these things and not get confused about why what you want didn't happen. Okay, so why can't I close this? Hey, close it. So any questions or comments while I'm trying to figure out my recording problem? No? You guys can talk amongst yourselves while I figure this out. As long as I record it, that's what's important.